Hello, everyone. I would say good to see you, but I don't get to see you. Hopefully, it's good to see me. I don't know. I'm just going to continue on my merry way, talking to my computer here about some calculus. Hopefully, we got caught up in class and have learned some stuff in class too. So, today we do section 4.3, which are the derivatives of the inverse trig functions. So, if we were sitting in a class right now, I would ask you, do you know the derivative of y equals sine inverse of x, or cosine inverse, or secant inverse, or cosecant inverse, or any of those? I don't expect that you probably have these memorized at this point. It's been a long time. Hopefully you remember and learn them. I'm going to tell you all 6 of them. There are 6 inverse trig functions. There's actually only like kind of 3 formulas to memorize, though, because some of them are just opposites of the other. But I'm actually going to, before I just tell you, I'm going to walk you through how we get them. So remember, whenever we do new derivatives, we need to use old ways to find the new derivatives, okay? This is not a power rule, by the way, so be really careful here, just a little notation. Anytime you see that, it's inverse with a function, like a trig function. Another way to write it sometimes to avoid that confusion is this way. It means the exact same thing. If I wanted to write a power, I would write it like that. This would be a power rule. So if I wanted to find the derivative of this one, I'd be drop the power, -1 times sine x, subtract 1 to the -2, and then the derivative of sine, which is cosine. So you just have to be aware of context and how we deal with this, all right? So this little thing there always means inverse. It's not mean power, all right? So here's how we do it. The reason we did implicit differentiation yesterday was because we need implicit differentiation for this. So you may remember that inverses are just switching the x's and the y's. Hopefully you remember that. An inverse of a function is switching the x and the y's. So another way to write y equals sine inverse of x is x equals sine y, switching the x's and the y's, right? If I go y equals sine x, then its inverse is x equals sine y. So this notation now makes it a lot easier to do a derivative because we can use implicit differentiation like we learned yesterday. So the derivative of x would be 1. The derivative of sine y is cosine y, but because y is some function of x, we need times y prime. We solve this for y prime, and we get 1 over cosine y. Seems great. Yay, we're done. Easy derivative. But think about that for a second. We know what y is, right? Y is the sine inverse of x. So we don't want to leave y. Yesterday's homework and implicit differentiation, we left y alone because we didn't know what y was, but now we know what y is, so we don't want to leave it there. But we also don't want to do this because this would get really messy. If I said 1 over cosine y, we get 1 over cosine y, we know is sine inverse of x. But that looks not very nice, okay? And we learn ways to deal with this in trig, formulas and half-angle formulas and things like that. It's not really necessary that you memorize all those formulas. So I'm going to draw a little picture to try to get back. So what I want to try to do is get this y right here back in terms of x, but not as complicated as that. So I'm going to draw a little picture here. We know that x is equal to sine y, right? So if this is y, and this is, so if we go, so y is an angle, right? So the sine of y is x. Remember, sine is opposite over hypotenuse. Little SOHCAHTOA. So opposite, it's x. So opposite over hypotenuse, which makes this equal to 1 minus x squared by the Pythagorean theorem. Okay, so that's our little substitution. Now we're trying to find cosine of y, right? We're trying to find cosine of y. We go back to my picture. There's y. Cosine is adjacent over hypotenuse. So that's going to be 1 over 1 minus x squared. Okay. So there's your kind of formula to memorize that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. I'm about to give you all 6. You could prove the other ones just like this. I'm not going to go through all of them. It's a nice little thing if you forget. You do need to know these. You do need to memorize these for sure. But sometimes you forget. You can always use this little method to get them back. And then I'll do a couple of example problems with chain rules, okay? So I'm just going to throw them all at you real quick. You got a video, so you could pause it right now. I'm not going to talk through it at all to the most part. I changed from x's to u's for a reason, because u's implies a chain rule. We're not just going to ask what the sine inverse of x is and be done with it, because that's only one question. So we're going to ask like the sine inverse of 3x squared plus 2 or something like that. So I have to use the chain rule. So hence why you see in here the sine inverse derivative is what we just did, right? 1 over the square root of 1 minus u squared, but then times u prime if it's the chain rule. You could put x's in there. It's totally fine. Just remember we have to do the chain rule. I'm not going to spend a lot of time because you can pause this. The cosine just has the negative sign there. It's the only difference. Tangent is 1 over 1 plus u squared. Sorry, I probably should have put these in better order. Cotangent is the opposite of that. Secant is 1 over u times the square root of u squared minus 1. And cosecant is the opposite of that. So there's really only 3. You do have to memorize them for the midterm for sure. For right now, just you can look at your sheet and that kind of stuff. So I'll do a couple examples with the chain rule so you can see it work. Okay. I got 3 examples here. I think we'll leave off that last one. It's a little complicated, but we'll do 2 of them. Okay. So this is a chain rule. So remember, we're starting with sine inverse of box or circle. So we start with that. We treat that circle as a chain rule. So we treat that like it's a variable for a second. So we just do sine inverse, right? So the derivative of sine inverse is 1 over the square root of 1 minus x squared. But x now is that whole function, right? So 3x squared plus 2 squared. So just for a second, that's the chain rule, right? We treat that like it's a function all by itself, like it's an x. Now we just need to do the chain rule. So I've applied the sine inverse rule. So we just do times the derivative of what's inside that circle, which is 6x. Just leave it like that. Same thing as always. Don't do any simplifying. A little too complicated. So this is a crazy one. Don't worry about that one. But we'll do this next one, and then we'll be done. Let's change this, actually, since we just did sine. Let's change it to a, I don't know. Let's change it. What do I want to change it to? We'll change it to a secant, because that's the most complicated one, maybe. So we'll go secant inverse of 3x over x plus 2. So same start. First, this is a box. We just treat it like it's a variable. So the derivative is, we're going to do the derivative of secant, which is 1 over u, which is this whole function. So 3x over x plus 2 times the square root of u squared, which is 3x over x plus 2 squared minus 1. This is let me change the color here. That's like my u, and that's my u squared. Just leave it alone. Don't do any simplifying. Nothing else to do. All right. So now I have to apply the chain rule piece of it. Remember, I treated that like it's x. So now I have to take the derivative of that, multiply it by that. That's the chain rule. It's a quotient rule. Derivative of the top is 3 times the bottom minus the derivative of the bottom, which is 1, times the top, all over the bottom squared. Leave it alone. No simplifying. Don't drive yourself nuts. The only issue with not simplifying is if you look in the back of the book right now, you'd probably see a different answer because they're going to simplify it. But that's just a lot of extra time for you that I would prefer you not do. It's better to do more practice problems at the trig inverses. So probably worth a little looking at the sheet, trying to memorize. The more practice problems you do, the better. I might not have given you a whole bunch of them, but it's hard to remember them without practicing them and doing them. So that's the inverse trig functions. Let me know if you need help on any of that, and we'll see you the next time.